everyone. My name is Gal, and today I'm going to talk about the neural mechanism underlying working memory updating. So working memory is the cognitive mechanism that enables retention of information over short terms and its online manipulation. Many daily high-level activities require working memory, and the stream of information is rich and constant. However, working memory is limited in its capacity, estimated around 3 to 4 items. Therefore, control over the content that enters working memory needs to take place. Task-relevant information should enter, while irrelevant information should be filtered out. A central theory in the field, proposed by Frank and O'Reilly, suggests a gating mechanism that separates between the sensory input and working memory. And the gate is closed by default, enabling robust maintenance of the updated information. Transient opening of the gate enables new information to be updated to working memory. Previous behavioral work has established that working memory updating is not a single process, but carried out by a cascade of sub-processes. First, we should open the gate to working memory. Then, we should identify the information as relevant, open the gate to working memory, replace the information within working memory with a new one, and reclose the gate to enable the robust maintenance. So today I'm going to talk about my work on the neural correlates of working memory updating, and specifically I'm going to talk about the dissociation between opening and closing the gate. Briefly, in neural terms, the gating model I just mentioned described theoretically the gating mechanism as a neural network of connection between the prefrontal cortex and the basal ganglia. And the gate opens while there is a phasic dopaminergic activity from the striatum. This activity inhibits the substantia nigra, causing disinhibition of the thalamus and excitation of the frontal posterior loop, and enabling the new information to be updated. To distinguish between working memory updating subprocesses, we employ the reference-back paradigm designed by Lubashevsky and Kessler. And in each trial, a face presented to the participant, framed in red or blue. The participant asked to decide whether the face he sees identical to the face presented in the most recent red frame. Let's see an example. Here, he should say different. Here, he should say same, different, and same. Okay? So the reference back task composed with two trial types, reference and comparison. In reference trials, the participants should make the decision of the identity of the face and update the current face to working memory in order to use it as reference for future trials. And in comparison trials, they only should do the decision without updating the current face to working memory. Reference trial require the gate to be open so the information could enter, while comparison trials require the gate to be closed and enable the maintenance of the face in the most recent red frame. Opening and closing the gate is a function of switching between trial types. Switching from reference to comparison require the gate to be closed, and from comparison to reference to be open. We analyze the task performance on 3 predefined contrasts. First, update cost, defined as the difference in performance between reference trials and comparison trials, which means we measured mostly the extra updating process. Gate opening, which is defined as the difference between switch trials and repeat trials. And gate closing, which is defined also as the difference between switch and repeat only in comparison trials. 61 students participated in this experiment. 13 were excluded due to technical problems, massive head movements, or low accuracy rate. First, we had an anatomical scan, then the participants completed one back task used as a localizer of their FFA later, and 4 blocks of the reference back as I just described. Let's take a look at the behavioral results. So the red line is the mean reaction times for reference trials and switch or repeat. And the blue is for comparison trials, switch and repeat. And as you can see that overall, reference time were slower than comparison trials, and this is refers to the extra updating process needed to be in the reference trial, not in the comparison trials. The difference between switch and repeat, I'm doing with my finger. The difference between switch and repeat in the reference trials found to be significant, and this is actually refers to the gate opening, and the same in the comparison trials refers to gate closing. Now I'll show you the fMRI results, first for update cost and then for the dissociation between gate opening and closing in each of the areas I presented earlier. Okay, so first, the frontoparietal network, the frontal gyrus highlighted in blue and the parietal lobule in pink. And as you can see, we found significantly more activity in the frontoparietal network during reference trial rather than comparison trials. Also, RI analysis on the basal ganglia revealed that the globus pallidus found to be activated more during reference trial rather than comparison trials. And the FFA, the posterior cortex that we extracted from the localizer of our participants, also found to be active during a reference trial more than comparison trials. The thalamus found to be as well. Now let's take a look at the dissociation between gate opening and closing. First, the frontoparietal network. On the left, we can see the results for gate opening, and on the right for gate closing. The upper row refers to the frontal gyrus, and the down is for the parietal lobule. And we can see that on frontal areas, we found quite a large dissociation in the activity between gate opening and closing, but not in parietal regions. There is almost symmetrical activity during these two cognitive processes. RIF, the basal ganglia, revealed that during gate opening, we found a full activity of all basal ganglia nuclei, while not in gate closing at all. Thalamus found to be activated during gate opening and not closing as well. And the FFA analysis that we used from the localizer found to be more activated during gate opening, but not during gate closing. So to conclude these findings, first we support the gating mechanism proposed by O'Reilly and Frank, and we found dissociation between gate opening and closing. In neural terms, we found activity in this frontoparietal posterior striatal loop, while during gate closing, we found only activity in some parietal areas. Consequently, we found that we found a neural evidence for the hypothesis that the gate is reclosing passively. We didn't find any striatal activity during gate closing, which means the gate is passively closing, as the hypothesis of this model, or there is a mechanism that yet to be known. And this is also a hint for my upcoming project. And next, also, we would like to explore further the FFA activity that we saw here, the posterior activity, and to understand what is the relation between the low-level activity, perceptual activity, and updating working memory, and the neural mechanism underlying procedural working memory and not only declarative. And this will be all, and thank you. And I have only 3 more minutes. I did it really fast.